Implicit differentiation is pretty different from the types of derivatives we've been doing so far, and that's because it's used specifically in cases where you're not explicitly defining your function in the form of f of x equals and then several terms that have an x variable, right? Instead, you'd want to use this in cases where you have x's and y's, or multiple variables scattered throughout your equation. One example that's very common in showing people how to do implicit differentiation is dealing with the equation of a circle. So you might not remember, but the equation of a circle looks something like this. X squared plus y squared is equal to the radius squared. And I'm just going to use the number 100, which would imply a radius of 10, right? The square root of 100 is 10. Now, how could I find the derivative of this function, right? Or sorry, it's not actually a function, right? It's the equation of a circle, which by definition is not a function. It would fail the vertical line test. And that's one way in which the situation differs from the previous examples, right? This is not a function. Now, how do I take the derivative? Well, what you have to do first with implicit differentiation is take the derivative of both sides of the equation. So what I'm going to do is take the derivative, and I'm asked to find it with respect to x, just like we typically would, d dx of x squared plus y squared, and on the other side I'll do the same thing, d dx of 100. And remember, we're finding the derivative with respect to x because x is your horizontal direction. We're looking for the rate of change, right? Y over x, the change in y over change in x. That's why we're taking the derivative with respect to x, even though there's two different variables in here. The derivative with respect to x is what we're interested in finding. So we d dx both sides. What comes next? Well, now we just take the derivative of everything that we have with respect to x. What's the derivative of x squared with respect to x? Well, that just means we use the power rule, right? X squared, when you take the derivative, it becomes 2x. Now, what's the derivative of y squared? Well, you might say, let's just use the power rule again. Let's bring that 2 to the front, and you would be right in saying that, 2y. However, that base that's normally x is not x. Instead, it's y. What do we do when the place where we usually see an x is something different? Well, we use the chain rule, right? We multiply whatever answer we get by the derivative of that inside part. Well, what's the derivative of y with respect to x? Well, it's dy dx. So all you have to do is derive this the way you normally would, but because it's not x, you put dy dx next to it. That's it. Now, on the other side of the equal sign, on the other side of our equation, we have to take the derivative with respect to x of 100. Well, we've already talked about what happens when you take the derivative of a constant, of a number. It comes out to 0. Now, our goal is to find the derivative with respect to x. Our goal is to find dy dx. That's what we want to find, right? Because normally, and if I haven't made this clear yet, I apologize, when we find the derivative of something, right, when I say f prime of x, if we have an f of x function, really what you're doing is you're taking the derivative of that with respect to x. Remember, f of x is actually equal to y. You're finding the change in y over change in x. You're finding the rate of change. That's what's going on here, dy dx. Well, we happen to have a dy dx in our equation. Let's solve for that dy dx. How do we do that? Well, that 2y is stuck with it, so I'm going to put that with it. But that 2x we can move to the other side of the equal sign, minus 2x. So we're just doing a little bit of algebra to isolate the dy dx. Now divide both sides by 2y. So dy dx is equal to negative 2x divided by 2y. Further, we can simplify that. Dy dx is equal to negative x over y. Meaning that if you think about what this graph illustrates, and I'll do a very crude graph, this is a circle. It looks something like this. and it has a radius of 10, meaning right here you have the point 10, over here you have negative 10, up here you're at a height of 10, and down here you're at a height of negative 10. That's what this looks like. What this means is that the slope of a tangent line to any point on this graph is going to be equal to negative x over y. So if you're thinking of this tangent line here, what's the slope of this? Well, you can look at what these x and y values are at that point, and whatever they are, you simply say negative x divided by y, whatever those numbers are, and it will give you an answer that equals the slope of that tangent line. And it makes sense that it's negative because it's going downward, right? If you think about some simpler examples of points on this graph, you might think of a point here at the top. We know the slope of the tangent line at the top of a circle is 0, right? It's a flat line. And you could figure that out by using the x and y points, right? The x value here is 0. The y value here is 10. So what's negative 0 over 10? Well, it's equal to 0. The slope of that line is 0. If you try to do a point like over here, where the slope is a vertical, well, you plug in the x value 10, so negative 10, divided by a y value of 0. Negative 10 over 0 is undefined. And of course, the slope here is undefined. It's a vertical line. So this will absolutely work in finding the instantaneous rate of change of any point along the perimeter of this circle. All you have to do is plug in the x and y values at that particular point. So that's the application, and that's why we need to know how to use implicit differentiation. Now let's look at another example. Let's say we want to find the derivative, the dy dx of 2x squared minus 3y cubed is equal to 5. Okay, we're going to start the same way we did before. We will take the derivative with respect to x of both sides. Okay, now, how do we do this? Well, on the left, the 2x squared will simply become 4x. And then you'll have 3 times 3 is 9y squared, like that. We're just using the power rule, right? But remember, this thing here is not simply x, it's actually y. So we have to use a chain rule. Remember, the implicit differentiation process is heavily dependent on the chain rule. It just looks different than how we usually use the chain rule, right? So we multiply by the derivative of y with respect to x, which quite literally is dy over dx. Okay. Now on the right-hand side, we know what's going to happen. The derivative of a constant like 5 is going to equal 0. So now we have to isolate for dy dx. So I can move my 4x to the other side. I would have negative 9y squared dy dx equals negative 4x. And then I'll simply divide both sides by negative 9y squared. So dy dx is equal to, the negatives will cancel one another out, 4x over 9y squared. This is our derivative. So I'm not positive what this graph looks like. You could graph it on Desmos and see what the shape is. But any point along that graph, if you want to find the instantaneous rate of change, you simply look at the coordinates of that point and you plug them in here for x and y. You calculate this and it will give you the instantaneous rate of change at that point. Hopefully that clears up implicit differentiation, when to use it, how to apply it, how the chain rule works with it, and how to use it in situations to actually find your instantaneous rate of change. You simply plug in the x and y values. Hopefully that makes sense.